Okay, I think that's on. So we continue. But before we continue, I wanted to recap where we left off. I know it's wet, but I can't bring myself to start on that side. I'm right-handed. I think this way, so I think it's okay. Okay, great. I'm getting a start and look from over in the corner. So okay.
Avoid the edge should be okay.
Yes. Okay. Okay. So as a reminder, as a pivot from what you heard about earlier, I'm talking about data analysis in particle physics and in the context of machine learning. Yesterday, I talked about parameter estimation, and today I'm going to talk about unfolding. And I'm going to tell you what that means shortly. Okay, so before I do that, I want to just recap, have my picture of like how everything works and what the setting is. So as a reminder, our goal is to figure out what is the theory of everything. Whatever the rules that describe nature, we do that by doing some experiment. We get some particles, either from a collider or from, say, direct detection or whatever we're doing. Then we have a detector. We get measurements. And then we get reconstructed particles. And yesterday, I wrote observables at the bottom, because I said we can't work with reconstructed particles. The dimensionality is too big. We do observables. Yeah, I cast that away. The point of machine learning is to use the high-dimensional objects directly. So I'm not even gonna bother writing it today. Okay. And we want to do inference. So over here, we have our theory. And it has some parameters. And we have the same path, basically. And yesterday, I talked about how to do inference. We're at this level. That was yesterday. Looking at the reconstructed particles at the end of the chain to infer the parameters theta. And today, the goal is to talk about how we can go back to this step and compare at the level of particles before the detector. And the reason that this is interesting is because once we remove the detector distortions, the result becomes independent of the detector. I don't need access to the data, and so anyone at any time can do the inference step. And you could apply all the same tools as yesterday, but to data that don't require access to the detector level data. Okay, and so also notation, I'm going to call this z, and I'm going to call this x. Okay, and I think that is all I want to say about that.
Question?
Yes.
So if you're throwing out observables and staying with particles,
Yes.
then don't you risk your machine learning something that is badly IRC unsafe?
Yeah, so it could be that you want to use certain information because you think the information is better for some reason. Like let's say your calculation only includes certain physical effects. Like for instance, doesn't include things that are not IRC safe. Then you might want to parse this information, but you can do that in an automated way. So let's say you want to use an IRC stands for information you're safe. So it has some nice theoretical properties. Then instead of using observables that people are running down over the last decade, you should use a neural network that's IRC safe. Or let's say you want something that's Lorentz. Your requirement is you should impose it on a neural network and not on a basis of observables. That can be done. I won't talk about that. I'm happy to discuss it offline, how you do that. But that can be done. Yeah. OK. On the same page? Excellent. So what we want is we want to be able to measure differential cross-sections. This is sort of like the bread and butter of particle and nuclear physics. What is a differential cross-section? I talked a lot yesterday about histograms, so I'm going to draw a histogram. We do a histogram, dn, dx, or OK. Oh, yeah, let's say x is one-dimensional here or something. We have histogram. And we have some data points. Okay, so actually, you know what? I'm going to start with. Okay. As with yesterday, I'm going to start today with the classical approaches, and the classical approaches require observables, and then I'll generalize it. So, okay, we're still stuck with observables for a little bit longer. So, the classical approach would be make a histogram, and I want to make a cross-section. Okay, so a cross-section looks very similar, except it has units of cross-section. And I don't know, it looks kind of similar. Blah, blah, blah. I'm gonna, okay, just be quick about it. Okay, so the classical approach is to use histograms where I have a low-dimensional observable and I represent the probability density as a histogram. And so here is the counts. I just have counts of my observable. And over there, I have the counts at particle level. So the z is at particle level. And so this object doesn't depend on the data, on the detector level data. It's like the true spectrum of particles I should get. And in principle, this can be calculated. This cannot be calculated because it requires a detector simulation. This, you can calculate it in principle using your favorite calculation methods. And it has units, you know, the right units of say, you know, barns per whatever x is. Okay. So yeah, this is like detector level. That's particle level. And classically, for most analyses, but not all of them, the f is the same. So like we have some observable, we have our particles, we apply the same f to get the same observable in both cases. Okay, so oh, thanks. Yeah, it doesn't make. In fact, it should be du. Over here too. Yeah, you're totally right. Okay, thanks. Okay, and then once I do this, like I have histograms, and I told you yesterday how you can do inference with histograms. So all the same machinery just applies. So this is great because anyone can do inference. Like once you have this, I can make a calculation. I can run Pythia. I can make predictions for some parameters. And there are thousands and thousands and thousands of bins in, or maybe hundreds and hundreds of measurements that are public. You can go to HepData. HepData is like a great repository for particle and nuclear physics, and there are a bunch of measurements. And also, you can compare directly to experiments. So at this level, you can't compare two experiments, because if the detectors are different, you get different answers. But here, I've removed the detector, and so I should be able to compare experiments directly. OK. The challenge, which I'm going to spend a little bit of time talking about, is that going from here to here is an ill-posed problem. And I'll explain in a minute what I mean by ill-posed. But we're going to do as best we can, given that constraint. OK, so we want to do, so going from here to here, we call it unfolding. In statistics, they would call this deconvolution. So convolution is like smearing, going from particles to measurements. And backwards is deconvolution. So yeah, unfolding, deconvolution. So the first step in any cross-section measurement, and prediction for that matter, is you specify your event selection. Because you can't calculate everything, because all the cross-sections diverge. So you want to say, I have an event selection. So that's the first step. You say, I'm going to measure or predict the cross-section of top quarks with some PT above some, transverse dimension above some value, and with some rapidity range. And you have an event selection at the detector level and at the particle level. At the particle level, it's called the fiducial volume of your measurement. Usually, this is not this cross-section is in some fiducial volume. OK. And then unfolding has to do 4 things. So one is it has to remove the background. Because the calculations that we make are always with respect to some process. And so if there's another process in the data that you don't care about, you want to remove it before you unfold. Then we need to correct for events that pass RICO not true. So let's say you have some events that pass your detector level selection, but not your particle level selection. They're sort of like fake events, if you like. They could be from pure noise, but more likely than not, they're like, let's say you have a threshold, like I require events to have a momentum above, say, 20 GeV. And you could have particle level events at 15 GeV that smear above 20 GeV, so they would pass your detector level selection, but not your particle level selection. And we have to do something with those events. So that's that step. Step 3 is the correct for distortions, resolution effects. And most of this lecture will be about that, because it's the biggest thing you have to do. And then 4 is the converse of 2. So correct for events passing true, not RICO. OK. So most, like I said, I'm going to focus on that one, because that's the biggest effect. And the larger the fiducial volume, the more inclusive your selection, the less the other things are a problem. So if you make a really big fiducial volume, you can't migrate in and out of the fiducial volume, because everything is in the volume. OK. All right. So first, classical unfolding. So when you have histograms, basically you could think of a histogram as a vector of bin counts. And so when I think of it as a vector of bin counts, it just turns the problem into a linear algebra problem. So I have some vector of bin counts, the measured ones, and that is just some matrix times the true ones. And this is called the response matrix. So I have some particle level bin counts, some measured detector level bin counts, and there's a matrix that describes the probability of measure in bin I given produced in bin J. Something like that. OK, thank you. OK, so yeah, that's the response matrix. And in classical unfolding, that's the most important object. Now, this is just step 3, just describing the effects of step 3. More generally, if you want to write the full shebang, which I'm just going to write down once, it's something like this. No. It should be something like maybe with a B or something. So if you want to account for all the effects, so here you have all the truth events, but then if I correct for the ones that pass the truth but not the RICO, so I basically get rid of them, then I multiply by the response matrix, I add the background, and then I correct for the ones that pass the RICO but not true. OK, that's kind of a mouthful. And I'm basically going to ignore F, E, and B for now. I'm going to focus on that problem. It's hard enough. And then I'll revisit at the end how we solve the general one. OK. So back over here. OK, so it's a pretty simple linear system. You might be thinking to yourself, if that's my equation, why don't I just do the obvious thing and be done with it? OK, that's like how I solve linear equations. And that doesn't work for 3 reasons. One is that often R is not square, so I can't take its inverse. And that's kind of a technical, that's I mean, there are ways around that, obviously. More importantly, R is usually not invertible, so I can't take its inverse. R describes detector distortion, so there's actually information is strictly lost going from particle level to detector level. It's a smearing. It's not just a shift. If it was just a shift, it's no problem, but it's actually a smearing. So I can't do that. And the third is that cross sections are non-negative. So if I took this, there's no guarantees that the solution will be non-negative, and that would be unphysical. Okay, so this is not what we do. And instead, we do like various forms of regularized matrix inversion. Okay, yeah, so I just write it down to be clear. So R is not square. R not invertible. And I want R inverse M not negative. Okay. So we want to instead get around that, and we do that with regularized matrix inversion. So let me write down a revised solution. Okay, so yeah.
Why can we assume that R is linear as opposed to just some general function of the truth values?
Yeah, so the question is, can we assume that the problem is linear? And so in this case, R is just, like you always produce it in some bin, and it has to be measured in some bin. So R just describes what's the probability that you measure it in some bin given it was produced in some bin. The actual detector response as like a function, stochastic function, is usually not linear. But as a matrix equation, it's linear. I'm just describing you measure in bin I given it was produced in bin J. So that part is linear. It's just like a sum of probabilities. Because every event is independent, and it has to go somewhere. So it's just like a multinomial. Yeah. Okay. Okay, so the revised solution, or a revised solution, is the following. I'll just talk about it for a second. Okay, so basically this is, I want to find the t prime that is as close as possible as being the answer to the inverse problem. Where this here, t is a vector, but I'm basically saying, look at all the non-negative t's and find the one that's as close as possible to solving the problem. Except there are two twists. So there's this matrix thing here. And that's because you can throw in the uncertainty on M if you wanted to. So sigma here is called the covariance matrix, and it encodes the uncertainty on the measurement. You could also just make that diagonal, and it would still be an interesting solution. And the other new piece is this last one, which is a regularizer. And so lambda here is a hyperparameter, and delta is a function that imposes some constraint on the solution. So classically, for solving problems like this, you would impose like smoothness constraints on t prime. So you'd say like, I don't want it to oscillate too much. And in fact, when R is very badly conditioned, then the matrix inversion solution oscillates a lot. And so by imposing some regularity, like that it's smooth, for instance, then that helps with that problem. But a more common a constraint would be something like the following. Where let's say t0 with uppercase 0 is the starting simulation. So I have some, pains me. I have a prior, sort of. It's not really a prior. It's just I have a starting simulation, and I say I'm not allowed to move too far from that. That's what this would do. And in fact, if you use this solution with that constraint, this has a name. It's called t-unfold. And because you're a room full of theorists, I assume almost none of you have used root before. Not only are you theorists, you're also in the 21st century, so you haven't used root before. But if you have used root, if you're a poor soul who's used root, you know that in root, all the classes start with T. So T unfold is yeah, that's why. Okay. All right. I'm not going to talk about T unfold anymore. I would say, roughly speaking, this has like 30% of the market share of like all measurements done so far. Yes?
Is there like a particular reason I would use a squared regularizer instead of like an absolute value or something else?
Oh, yeah, okay. The question is there any reason I would use a squared regularizer as opposed to an absolute value? So I should say, I'm being a little bit cavalier here. A T unfold is sort of like a whole class of models that have, and there's a bunch of hyperparameters, and one of them is like exactly how you impose this regularization. Yeah, and in principle, that's something you have to figure out in the actual cross-section measurement. You try to figure out, for your region of phase space, what's the best regularizer. Yeah. Say it again? Lambda is a constant that you have to tune. Usually you would tune it, like in your region of phase space, you'd say, I want to achieve some precision, and my resolution is such and such, so I need to make lambda. Like if your R matrix is really, really bad, you might want to make lambda stronger to regularize it more. So the financing depend on lambda? Definitely, yeah. And in the end, it's sort of a bias variance trade-off. So when lambda is 0, there's no bias, but there's a lot of variance. And so by turning on lambda, you're introducing a bias, but you reduce the variance. And ultimately, that trade-off is application specific. Okay, so another example, which I would say has maybe like the rest of the market share, is an iterative approach. I guess I'll put it over here. It's OK. I'll write really big, though. And this one is the most popular. And this one, it's iterative. So it has the following update rule. Where did I put the little ends? OK, so here the idea is you have some starting simulation, T0. That's usually the actual simulation, but it could be anything. In principle, it shouldn't depend on what you pick, although in practice it will. And then you update. So you're going to update n times. And the update rule is to use basically the posterior at step n multiplied by the data. And in terms of the quantities over there, this would be this thing. What did I call it? OK. And so basically, you have the response matrix, Rij. You have the previous solution, and you have the new solution, the data, Mi. OK. And this gives you a new truth that you can then basically repeat over and over again. So this procedure, and you usually stop at some point. So you say, put this up a little bit. OK. So usually you stop after like a few iterations. And this is called many things. It should be truth J measure I. Thank you.
And what is it? Rij, Tj, the whole thing together as well?
This?
Yeah.
No. So Rij is a constant. Rij is just the response matrix. It doesn't depend. So this looks like this is like the posterior after the n-1 step, which is exactly the fixed response matrix updated with the prior from the previous step. Yeah.
There should be a residual index on the left-hand side that I don't see on the right-hand side.
A summing over I. So
But there should be a j left
there should be a j left. The j is here.
in the next line.
In the next line, there's a j here.
But there's
Oh, I think that's OK.
Is that J summed?
Oh, yeah, that's a problem. Thank you. Yeah, that's true. what's my problem? You are right. That is a mistake. Yeah, there should be residual j. There's a mistake. Let's see if we can figure it out in real time.
For sure, maybe it's RJI because we merged it through J measure I.
Well, yeah, I skipped some steps between here and here to like use Bayes' theorem to like get it in terms of, because I have to go the other way. So this is truth given measured, but the thing that's universal is measured given true. That's the response. That's the response, right? And so that's why I'm rewriting it in this way. Okay, yeah, it's okay. That's good. So
J isn't the sum, it's just a sum index.
say it again.
The J isn't the sum, just
The J is not.
yeah,
J is not in the sum.
yeah. You don't sum over J.
I'm not summing over J. Oh, yeah, very good. Thank you. We're all used to Einstein notation. There's no sum over J. Yeah, thank you. Okay, yeah, I was really confused. You're absolutely right. I'm only summing when I'm explicitly summing. Thank you. So there are two J's here, but I'm not summing over them, so it's, yeah, okay, good. Okay, thank you. Okay, so this thing has a name. It's called Lucy Richardson. And it was invented by astronomers a long time ago. And it was reinvented by particle physicists, and they called it, I guess, called it iterative Bayesian unfolding, which is a horrible name because it's not Bayesian. But OK, we're stuck with it. So I'm going to call it IBU. This procedure, you can prove, converges to the maximum likelihood estimate. So if you wrote down the likelihood, which is the product of Poissons over all the bins, this procedure, if you run it to infinity, would give you that answer. And the reason you don't want that answer is because it has all the horrible problems of matrix inversion. And so you stop at some point. Like I said, usually like 3, 4, 5, something like that. OK. So I find the rule to not be very illuminating, like exactly what it's doing. I mean, you can see what it's doing, but I like to write it down in 2 steps. And the reason I'm going to do that is because it's going to generalize to the, as you might guess where this is going, it's going to generalize to the unbin case better. So let's rewrite IBU. OK, so there's 2 steps. Step 1 is going to be the predicted I counts. So for a given truth distribution, I can write down the predicted counts in a given bin as this one. This one should actually be summed over J, I guess. So the number of counts in a particular measured bin, now the sum is over the truth. It's that number. And I assign a weight. I assign a weight to the simulation that basically corrects for the difference between the predicted and the true and the measured. So my measured in a given bin is mi, and my predicted is that number. So if I make a new histogram where every bin gets that weight, then my simulation will look just like my data by construction. OK? I'm running out of room for step 2. But I will try. Step 2 now acts. So this acts on detector level, and step 2 will act on the particle level. And maybe I'll just make this a little bit. Okay, divide by. so now I want to, in a given truth bin, in truth bin J, weight each event. So I look in a given truth bin, and I see which events they correspond to at detector level, and I assign the weight that corresponds to it. So if you like, I have these two data sets, the detector level data set and the particle level data set. I make weight based on the detector level one, assign those weights to the particle level data set. And so this would mean that my new particle level prediction would be the fraction of truth events that landed in Rico bin I times the total number of truth times the weight. So basically I say, I take my, my truth, this is my current truth, and I ask how many ended up in a given Rico bin, and then I assign the weight of that Rico bin. Okay. And so that would be, look familiar? And so that formula is the same as the one I wrote over there. Okay, so this took way more to write down than the update rule over there, but they're the same. But writing it in this way, it will be, you'll see in a second how it generalizes. And so we have a step one acts at the detector level, and step two acts at the particle level. Make this is abstract, so to be totally clear, I want to give a very explicit example. So let's do an unfolding. Okay, so let's say my response matrix looks like this. Let's take the simplest possible case. The simplest possible case is that the observable takes only two values. I'll call them 1 and 2. And in this super simple case, the true value 1 is always measured as 1. And the true value 2 is measured half the time as a 1 and half the time as a 2. Okay, so this is a pretty crappy response matrix, but it's very illustrative, so I'm going to use it. Okay, and let's say that the data that I observe in my detector now I'm going to get fancy. Is 50%. And for those of you really good at mental arithmetic, maybe you already know the answer, but don't say it yet. We're going to work through it, and you'll see what the answer is. Okay, so let's go over here. Now, in principle, it shouldn't matter what I start with, the starting simulation. But just for fun, let's say that my starting simulation is 50-50 at particle level. So like this. And I'm going to say, so red is particle level, and blue is going to be detector level. I think this is the fanciest I'm going to be during these lectures. So if that's my response matrix, then all the ones, oh, I guess I should label them. All the ones stay as ones, and half the twos become ones. So the measured one looks like that. Okay, so now I want to know what is, how do I proceed? Okay, so maybe I'll write it right here. Okay, so iteration 1. We'll do it right here. So iteration 1, step 1 over here, and step 2 over here. OK. What did I call? Particle levels red. I use different colors in my notes. That's the problem. I have to translate it in my head. OK, so particle level is 50-50. OK, so the rule is that I say I want to correct the blue to match the data. So the data is 50-50. So that means I have to assign a weight of 2/3 to this bin and a weight of 2 to that bin. So those are the weights I'm going to apply. OK? And then I note that so the events here, they came from 1, these came from 2, these came from 2. Okay. So now for step 2, I want to assign the weights based, oh yeah.
I have a question. So if we have an equal, or sorry, if we have an even mix of 1 and 2 types of true, wouldn't we end up getting 3/4 of type 1 and 1/4 of type 2, not 2/3, 1/3?
So it's possible I made a mistake.
Using that matrix R right there.
So it would be, oh, did I say 2/3, 1/3?
Or I see it on the board.
Yeah, sorry. So, okay, so you have, let's say 50-50. So half of them, so all the ones here stay here, and half of them go here. So you'd end up having, yeah, 2/3, 1/3, right?
No, it's 3/4, 1/4. See, what
So
one
here
is
I have,
3 times
yeah,
50.
50% times 1 plus 50% times a half. Which is, yeah, okay, yeah, you're right. Yeah.
2/3 and 1/3 is the weight, not the weight correct to the data. It's not
That's true. Yeah. Well, here I haven't actually assigned anything. I've just drawn the picture. So you're absolutely right. But I hope first I'm not on the hook. So yeah. So you're absolutely right. It should be. So yeah. I'll label the heights here. That's 1/4, and that should be 3/4. Yeah. Okay. Now you agree with my picture. Okay. My picture is so crappy. It's definitely consistent with that, I think. All right. I think the weights here are correct. So I want to go to here. I want to go from the weight should be 1/2 divided by 3/4, which is 2/3. So that's correct, right? So I think my weights are correct. This step is correct. You agree? Excellent. OK. Thank you for catching me on the arithmetic on the first one. So good. So that's that one. These are the weights. So now I have to figure out what would be the inherited weights. So in the first bin, I have whatever I said. It's half of my weights, half of my events get a weight of 2/3. So it'd be like 1/2 get a weight of 2/3. So that would be whatever it is, 1/3. And for the second bin, they have to add up to 1, so you know it's going to be 2/3. But I would have half of these get a weight of 2, and the other half get a weight of 2/3. And if you get 2/3, so this would be like, is it blue? No. So this would be like 1/3 and 2/3. OK, so here it was, they started off 1/2, and now it's 1/3 and 2/3. So this one is twice as high as that one. OK.
It looks like they're up. They were flipped or opposite. Is that opposite directions you'd expected, with the 2 being higher than 1, not lower?
Yeah. So the reds over here, they started even, and then so at detector level, there's migration to 1, but at particle level, you see it. Yeah, it pushed more events in 2. If my detector was like a better detector, and it was 1-1, you'd expect the trends to be the same on both. But yeah, that's not the case here. Basically, I have to uplift more 2 in order to match the data. Okay, and it looks like I'm going to do one more step. You can see arithmetic on the board is not my forte, but that's OK. All of you are checking me, and we'll get to the answer. OK, so we'll do one more iteration, iteration 2. And so we're starting with this. So we have 1/3, 2/3. And now I want to push this. What is it? Am I supposed to do red, blue, blue? I want to push this back to the detector level. So all the 1/3 stay there, and half the 2/3 go into the first bin. So it would be like, now I should just not do it in my head. I should say it's 1/3 plus 2/3 times a half. OK, so that's 2/3, right? So that would be. So now it's in fact like the inverse of that one. And then I can say, OK, now I want to match this with the data. And so I have to downweight this one and upweight that one. So this one gets a weight of 3/4, and this one gets a weight of 3/2. Because this would be 1/2 divided by 2/3, and this is 1/2 divided by 1/3. That's where these numbers come from. And I'm not even, OK, I'll just tell you what the answer is. The answer is 1/4, 3/4. Looks like that. Oh, shoot. OK. And probably you can guess the trend. So if you run this for infinity, you find, for those of you who could magically do this in your head, that actually at truth level, all the events are in the second bin. Which, if you know that, you just stare at the response matrix, and now it's obvious. If all the events are in the second bin, you get 50/50. OK. So that's how it works. So that was a very painstaking working through all the steps of IBU. But hopefully that was instructive to kind of see like how the update step works. There's the step 1, where we match the detector level. Step 2, we match the particle level by like inheriting the weights, pushing and pulling the weights between particle level and detector level. OK. I'm glad we're done with the arithmetic. That's the thing. That's absolutely the worst. And now I've been talking for a long time, and I haven't got to machine learning yet. So now it's time for that. I'm going to keep that on the board. So I'll go over here.
In reality, how well do you do the response matrix?
The question is, how well do we know the response matrix in practice? So very well. We have excellent simulations, but usually the response matrix is known within uncertainty. So R is like parameterized with some uncertainties, and you have to include that somehow. And I'm not going to talk about that. Yeah. OK.
There's another question over there.
Oh, yeah.
So if you treat like R as like T0 as a prior, and you do one iteration of this, and it's unbasable, and kind of posterior for your truth. So why is it OK to keep doing basal again and again and again after that?
Right. So yeah, the question is, if you stop after the first iteration, you have basically the posterior of the learned truth given the measured. Yeah, that's correct. And I'll say that explicitly in a second and again in different words. And the reason that you want to keep going, intuitively the reason you want to keep going, is because that depends explicitly on the prior. Now, you already brought in posteriors, and so I'm allowed to keep using posteriors and priors back at you, I guess. Yeah, that's right. So if you just get the probability of true given measured, it's prior dependent. And iteration basically removes the prior dependence. So in this example, if you want to have fun, you can start with a different prior, and you get the same answer if you iterate to infinity. But if you have the first iteration, you get whatever. It's very, it depends on the prior you pick.
So is this like a fancy way of being maximum likelihood?
This is, and I'm going to say in a little bit what it's called, but this is called the EM algorithm. and expectation maximization, which is a way of doing maximum likelihood step by step. Yeah. OK, so machine learning. There are a bunch of different ways of doing this with machine learning, but there are two very well-studied approaches. And they go by the name discriminative and generative. So discriminative machine learning is like a classifier, and generative is like normalizing flow, for example. And the prototypical algorithms in these classes, this one would be called omnifold. And this one does not have a beautiful name. I'm sorry. I know that people who study this are in the audience, but the latest incarnation is called ICINN, which stands for Iterative Conditional Invertible Neural Network. There we go. OK. Yes. All right. So basically, both of these procedures look exactly like this. But maybe you can already kind of smell what's going to happen, because I talked yesterday about likelihood ratios. And these depend on ratios of bin counts, which are basically likelihood ratio estimators. So that's what's going to happen. So I didn't leave myself that much room, but OK, I'll try. OK, so there's step one. Oh, I'm going to initialize. What do I call it? OK, so you initialize a weighting function at 1. And then step 1. In fact, this doesn't even really matter, honestly, the names of them. You have a weighting function, which is just the likelihood ratio. So the weight, the detector level weight at a given iteration is the ratio of the density between the density in data and the density of the simulation at that step. And what is the density at that step? I'm going to write it in the asymptotic limit, because that's easier to think about for me. So basically what this means is that I have a weighting function z, nu of z, and I take my events. My events in simulation come as pairs, xz pairs, truth measured pairs, and I assign to that pair the weight based on the truth. So nu of z gets assigned to the pair xz, and then I only look at x. So that's what this thing is. So basically, once you have a weighting function at truth, that induces a new distribution at the detector level, and then I take the ratio between the data and that new simulation. And as you might guess, I didn't specify anything about machine learning here, but you can estimate this with a neural network. And then you can easily make x be high dimensional. And in fact, I even somewhere just stopped using u and I went right to x. So you see, I already did that. Okay. So that's step one, which looks very similar to this, right? So the step one here was the measured over the induced measured. That's exactly the same here. This is the measured over the induced measured. And then step two, here we have a new weight. Basically, we have this weighting function, and I could assign this weight to the truth level events now. So now my truth xz pairs, I could just assign w of x to those. But I can't stop there, because now I have, at every point in my phase space, I have a bunch of weights. And a given z point could have a bunch of different weights, because the detector is stochastic. So a given point at particle level could get mapped to a bunch of different points at detector level, and they all get different weights. So that's no good. because I want my function to be a function. It better have a, for a given z value, it better give a single number. And so we just take the average. We say for a given point in phase space z, you take the average over all the wx's you get at that phase space point, which is exactly the integral of p sim of x given z n plus 1, which it's going to be OK, so if you just write out what this expectation value is, it is this, which is another likelihood ratio. It's basically it's the ratio of the induced truth divided by the original truth. So here there are two likelihood ratios. The step 1 likelihood ratio is between the data and the induced measured, and the step 2 likelihood ratio is the induced truth and the original truth. And then each of these can be neural networks, and you repeat the whole thing over and over again. Yeah.
What is the motivation to do this with machine learning as opposed to just doing this like iterative thing? Is it just like high dimensionality?
Well, it's still iterative.
So
and
the iterative without machine learning.
Oh, without machine learning, I probably would use the original formula I wrote down. I wrote down the iterative version of the classical one, so you can see how it generalizes to the machine learning case. But basically, the point is that this is equivalent, in the binned case, if x is a bin count, this is equivalent to IBU. And then here, I don't have to be bin count. It can easily be, a 1,000-dimensional object.
Okay, so the only reason is if you want to do unbinned. That's
Unbinned and high-dimensional, yeah, that's right. Yeah, those are pretty important motivations, but yeah, indeed, those are the motivations. Yeah, that's right. And here, for instance, x could be like a set of particles. And as long as I have a neural network that can process particles, I can easily get likelihood ratios and unfold everything. Yeah, and that is revolutionary in the sense that before, like, I don't know, a few years ago, every cross-section measurement ever produced was a histogram. And if I were to give a talk and say, I'm going to measure a 10-dimensional cross-section, I would be booed off the stage. And if I said 1,000 dimensions, forget about it. But now, that is happening. There are cross-section results that are starting to come out where the dimensionality is really large. The highest so far is like 20 dimensions. But 1,000 is on the horizon.
So when you say dimensional, that means how differential it is and how many different...
Exactly. The dimensionality of x, or z, yeah.
We probably can't compute that anyway, right, on the theory side, like a sort of 20 times differential cross-section.
It depends. Oh, you mean by calculate? And ultimately, like imagine I calculate a 1,000-dimensional cross-section, but then I can project to whatever your favorite dimension is. And you can probably calculate that. So the point is that this is now a more flexible object that allows you to pick things later. So for instance, suppose you make a calculation of some observable u, but you realize 2 years later, u tilde would have been much easier to calculate. Well, if you measured u, you're out of luck. But if you measured everything, I can give you u tilde, just like that. Yeah. All right. You can see my bias about which methods I work on because I left no room for generative models. But I am going to also try to recoup some space because it's equally as important and it can do exactly the same thing. So I will try. There's plenty of space up here. OK. So for generative models, it's also there's 2 steps, and basically the way it works is that in the step 1, the only difference is that in step 1, instead of learning a likelihood ratio, you learn a generative model. And you learn exactly the thing that Ricard mentioned, which is the posterior. So basically, you have some simulated sample of xz pairs. You weight it by nu, and then you learn the density, the induced density of z given x. That's the posterior. That's this thing here. So this is the central object in the generative approach. And then step 2 is basically the same as for the discriminative case. So there's n plus 1. Z is This is now data. So basically, we take this posterior, and this now says it's P of true given measure. So you take the measured from data, and for every measured point in data, you sample a true. That's what this integral means. And that gives you a new data set, a new true, and you take the ratio of the induced true with the original true. And that gives you a new weight. And then you can repeat. OK, so there you go. So to answer the question earlier about a maximum likelihood, the statisticians would call this step the M step, and they would call this the E step. So if you want to look up like expectation maximization algorithms, they're like a known tool for some likelihood, actually knowing the likelihood at any given step. And yeah, it doesn't really matter, but that's what it is. OK. So let me just briefly talk about some pros and cons. So I'll say discriminative, generative, pro, con. So formally, they do the same thing. You could use either one, and you get the same answer if like I said, they're formally doing the same thing. So the benefit of the discriminative model is that step one learns a small correction. It took me more symbols to write down step one, but it's learning a likelihood ratio between two things that are very similar. It's basically trying to make the simulation, tweak it a little bit to look like the data. So small correction. That's always good. That's step one. In contrast, the generative models, they have to learn the full density. So they're mapping, they have to learn all of P of z given x. And if you're using like a normalizing flow, basically that means mapping a Gaussian to your data. And if your data are not like a Gaussian, it's a heavy lift. Okay, so it has to do more work. So more work. At step one. OK. On the other hand, the generative models, you see that step one doesn't depend on the data. I only have to learn it based on simulation. So imagine I have very little data. So for instance, let's say you're doing like a neutrino experiment, and the neutrinos don't interact very often, so you don't have that much data. Then maybe this tool will be more appropriate. So you'd say, OK, so this independent of data at step one. In contrast, omnifold, or the discriminative models, they explicitly depend on the data. So they learn a likelihood ratio between the data and the simulation. And so if your data are very limited, then your step one weights will be very noisy. Limited by step one, by data. That's step one. Now, once you get to step two, it kind of gets washed out. Once you get to step two, they both depend on the data, and it doesn't really matter. And I should also say that for the generative models, the fact that you have to do more work, there are ways around that. So there are cool generative models that allow you to not go between, say, Gaussians and the data. You can actually go between, say, simulation and the data, where you don't know the explicit density. And so they're kind of like hybrid methods between the two. For those of you who are really curious and you want to look something up, the things to look up would be Schrodinger bridges or flow matching. These are just for the super interested. Those are machine learning models that are generative models, but you don't have to know the base density. OK.
Sorry, we are using the same loss function for both, right? The first one is the process.
Yeah, I haven't mentioned loss functions at all. Whenever I'm running a likelihood ratio, so here, here, and here, it's see yesterday's lecture notes. So you could use the binary cross entropy, f over 1 minus f, or you could use the MLC loss. You just get f directly. Whatever you have to pick that. That's hyperparameter, basically.
And regarding to the learning rate, can I compare like here between these two methods?
So in principle, you probably need to tune that based on the method. Like formally, as I've written it, they give you the same answer. But in practice, all the hyperparameters need to be tuned. Yeah. And in fact, the hyperparameters can be quite important here because it's an iterative method. So you have to train a neural network at every step of every iteration. So let's say you're going to run like 10 iterations. Now you have to train 20 neural networks. So you kind of want to get it right. Otherwise, it can take forever. OK. I'm almost at the end. I want to mention just a few things. So I basically ignored acceptance effects until now, but I want to briefly talk about how you would do them in the unbinned case. In the binned case, it's very straightforward. You can just apply bin by bin corrections, and that's very good. But there's no bins in the unbinned case, so that doesn't work. OK, so the first is, how would you subtract background in an unbinned case? So in the binned case, you have your histogram of the data, you can have a histogram of the background, and you can just bin by bin subtract the background. And then you can proceed as if there's no background. So that's great. But there's no unbinned version of that, or there's no direct unbinned version of that. Now there are a couple of tricks. And so I'm going to give you one trick, which can be used elsewhere. And so here's the trick. So for background subtraction. And for this, I'm going to write down the loss function you would use. So let's say, I'll just write it down. OK, so this is the cross entropy, the binary cross entropy, sort of. So here I have these three terms. And my claim is that if you take the data and weight it by the neural network that you get from this, you will have subtracted the background. So let me explain why that works. OK, so if I take, let's say I trained my neural network, it gets to the optimal, and I do the usual trick, f over 1 minus f. And now I want to figure out what is this going to be. So the numerator is just the density of the data. It's basically the first term. And the denominator will be from the combination of the second two terms. And that will be a repeat. So you see the third and the first term are the same data set. So it'll be the same here. But then you see that the second term, the log of 1 minus f, has a plus sign. So basically what that corresponds to is assigning a weight to all the background events of -1. Maybe I should have been more explicit. I could say, if it was regular cross entropy, there'd be a minus sign here, but I just put the minus sign. I gave every event a weight of -1. That's the trick. OK, so you can see that basically with this trick, now I have a likelihood ratio, which is the ratio of the data divided by, Oh yeah, again, this is what you get, but it's actually inverse of what you want. I think you want the inverse of this. You want the background subtracted data over the original data. So this is still a good object. You just take the inverse. OK. But you can see the denominator is the original data minus the background, and the numerator is just the background, or just the data, right? So if I weight every data event by this, it subtracts the background in an unbinned way. And in fact, this trick can be used anytime you have negative weights you want to get rid of. This will work. So let's say you do a high order calculation and it has negative weights in your cross-section calculation, but you don't want to have negative weights in your simulation. You can do the same trick. Basically, you just repeat the data twice, and then you throw in the negative weights, and it will get rid of them. Okay. Now, one thing I have to say about this is that background subtraction only works if the signal and the background don't interfere. And that may sound obvious to you, but it's very popular, for instance, to make predictions and measurements of top cross-sections, TT bar cross-sections. Differential cross-sections is one of the most precise calculations that have been made, and measurements. But in the measurements, people always subtract off the single top background. So for instance, you have you want to make predictions and measurements of this, and people subtract off this as a background. But actually, these have exactly the same initial states and final states. So this is not a good idea. But people do it anyway. So c'est la vie. But but not a good idea. So please don't do that. Yeah, it's of course harder to do calculations that include both. I think that's why it doesn't happen that way. Yeah.
So why is there not a sign flip in the denominator? Like if f is approximately n data p data, then why is that get the positive sign in the denominator?
Yeah, the reason is because in my term here, everything has the normal sign except for the background term. I put in a -1. So basically, I'm just assigning a weight of -1 to every background event. That's why it gets the sign flip. Yeah. If I had switched this to +1, it would be a plus there, which wouldn't be very useful.
Okay, but for the n data, p data.
Yeah, I could easily flip this to be minus sign by putting a minus sign over there. Yeah. If I put too many minus signs, then it would be a maximization problem, not a minimization problem. I haven't checked, for instance, that like the second order conditions are satisfied. Yeah. Okay. So then the very last thing I want to talk about, so this is for background, and the other thing is our acceptance effects, so the events that pass truth but not measured. So in this procedure, you see I relied critically on the fact that I have pairs xz. So if I have some events that pass one but not the other, this doesn't apply. This only works to correct for the resolution effects, where I have an x and a z, and they just got distorted. But what if I have events that pass one but not the other? In classical unfolding, you would just correct bin by bin, and that works fine, but once again, doesn't work here. Okay, so acceptance. Sometimes they're called acceptance and efficiency effects. I'm not going to distinguish them here. Okay, so for step 1, basically the way you'd modify it is the learning only uses events, or uses only events that have a measured quantity. So if you have an event that passes true but not measured, it obviously doesn't participate in step 1. Okay, so only use events that pass RICO. And likewise for step 2. Only use that passed true. And then I still have a little bit of a problem, because what weight do I assign? So I look at all my events, and I have to look at the weight from the previous step. What weight do I assign events that passed RICO but not true? They don't have a weight because they didn't have a truth event I could use to assign a weight. And you have a choice. So you could assign, for the ones that don't pass true, you could say, so don't pass true. You could say, one possibility is to just set the weight to 1, and that corresponds to just taking the prior. You'd say, for these events, I have no idea what I should do, so I'm just going to take the simulation. Another option would be to assign the average value. So you could say, assign the average for all the the measured values and that match that one, assign the average weight. And that might seem like a totally different answer, but because you're iterating this whole procedure, the impact of this choice decreases as you iterate more. And correspondingly, there's the same story at, I'll write it down, but it's the same story at step 2. Don't pass Rico. So you could assign, here it's W. Or you could assign, you could take the starting, whatever the starting one was, or you could assign, you could take the average. So this only works in the discriminative case. We haven't yet written down what it looks like in the generative case, but there's going to be like something very similar to this, presumably. Okay. Okay, I only have like 2 minutes left, so I'm at the end. Let me just make a few remarks. I'll use this one. So like yesterday, I am going to declare success. We now can unfold, we can make different cross-section measurements, unbind in as many dimensions using machine learning, which is awesome. That's what our goal was. We can compute bins and observables after unfolding, and we could even compute predictions for things that aren't even bins. So let's say, for instance, you want to make moments. I want to measure the moment of some observable as a function of, say, energy. I can easily do that. It's unbinned, so I can easily make moments, and there's no binning artifacts. So traditionally, when you measure moments, you have to, and let's say it's from a binned cross-section measurement, you have to correct for the fact that there are binning artifacts. But now there's no binning artifacts, so that's great. But there are challenges. Okay. So let me just end on this note. Okay, so I have a few challenges. So one is that everything I've talked about, both for generative and discriminative, they rely on likelihood ratios. Rely on likelihood ratios. The generative case doesn't depend on likelihood ratios at step 1, but on step 2 it does. So what happens if there's non-overlapping support between my simulation and the data? Well, then my likelihood ratios won't work. And so that's a problem. In practice, for a lot of the problems we care about, that's not a problem because, like for instance, QCD is very generous. And so the phase space is kind of filled everywhere. But there could be holes in the phase space that are real or fake in the simulation that could give problems. Okay, so that's an open research question. The other thing is that for most applications of machine learning, like training a classifier to distinguish cats and dogs or top quarks and gluons, you don't really care about being ultra precise. So if you train a classifier and you train it again and your answer differs by 1%, probably you don't care. But here we definitely care. And there are a number of reasons that we care, but let's say, for instance, that your systematic uncertainty is on the scale of 1%. Well, let's say you have 100 systematic uncertainties. If every time you also hit a jitter of 1%, then if the systematic uncertainty is 0, you'll see an uncertainty of 1% added in quadrature 100 times, which is horrible. And so we need to control the jitter in the neural networks to a level of like 1 per mil or better. And that's difficult. And right now, the solution is basically train a lot of neural networks and take the average, which that always works, but it's not very nice. So hard to be precise. In contrast, classical methods, they don't have this problem because they use histograms. And histogram is like a very strong regularization. And it does not try to understand the shape inside a given bin, and so it doesn't really care about that. Okay, but the most important limitation is that it's only as good as the detector sim. We don't really depend strongly on the particle level simulation like we did yesterday, but we definitely depend on the detector level simulation. And I'm going to put detector level simulation in quotes because also in top quark physics, but also elsewhere, there's a bad habit of measuring the cross-section of partons. So let's say you want to measure like the cross-sections of top quarks. So if you do that, not only are you unfolding the detector, you're also unfolding through the QCD of the parton shower, which is not a detector, and not that well understood. I mean, it's understood, but not very precisely. So that is a bad idea, I would say. But what can I say? It's done, so I'll say warning. I can see the utility, because I think all of you would like to calculate at the level of partons. And, but that's not what we measure. We measure particles. So you should make your prediction. Okay, so parton.